So the agenda of today, first of all, we are going to talk about Oracle Analytics Cloud. Then we are going to understand what is a data scientist and what is need to be a data scientist. And then how can we mix and match the two? So how can we become a data scientist with Oracle Analytics? So Oracle Analytics Cloud is the new tool from Oracle in the analytics space. Is delivered as a platform as a service. You don't have to do anything. You have to just go to the Oracle Cloud, select Start an Oracle Analytics system. You don't have to install anything, configure anything. It's all done for you. There are several purchase options, and also there is a huge discount if you bring your own license from on-premises. So on-premises customer, if they want to go to the cloud, they have a huge discount on the price of the analytical platform there. Functions. Oracle Analytics Cloud takes care of old school and new school analytic needs. So both the classic, where we were like 10 years ago when the business team was basically setting the requirements, writing down the requirements in a piece of paper, and then handing them down to the IT department, which was building stuff for them. Or the modern, where anybody from the business team can basically create their own reports based on any data source. If they can connect to a database directly, they will do that. If the data is on a Dropbox folder, they can also connect to that and start analyzing and creating beautiful visualization. The classic, as I said, old school, but still really valid if you want to provide a fixed way of navigating the information within your company. The end user experience is really similar to the one in OBIE 12c. So we have the repository, which is central, managed by the IT, where we define the metrics, the aggregation, the dimensions, the hierarchies. And then we have one or more set of interactive dashboarding where the end user can interact with the data, can change parameters, or they can also create their own analysis. We have BI Publisher for pixel perfect formatting, and we have the action framework that allows us to do drilling or navigating from one analysis to the other, passing spatial parameters. So it allows us to have a complex view about the information, the data in a company. The modern data discovery is the new trend, self-service. Everybody should be able to connect to almost any data source and to do data transformation and to create visualization. Oracle solved this with what they call initially data visualization, which is a component of Oracle Analytics. And they have within data visualization, they have two tools. One called Dataflow, which is the image at the bottom, which allows you to basically create ETL pipelines and change the shape of your data. And then you have data visualization, where you can create projects with almost any kind of visualization you have in mind. And the very good thing about this modern data discovery within Oracle Analytics is that it solves a lot of problems that back in the classic option, your IT department had to solve. Let's see some of them. First of all, Oracle Analytics, since it's a unique platform, allows you to do the best of both worlds. So you can have the centralized reporting, the unique source of truth defined by your IT department, and the specific access control. For example, if you need some sort of spatial security for some of the area, which is defined uniquely by the IT department. At the same time, within the same tool, without having to purchase 20 different tools, and having one unique control of the critical information within your companies, you have also the free discovery, the option to do data enrichment and cleaning with the data flows that we will see in detail later, and also the option to create insights on top of the raw data without having to ask the IT department to create a data model for you. All this is in a unique platform. You don't have to have separate purchases. You don't have to have every department with his own analytical tool. Everything can be managed with just one tool for everybody. At the bottom, there is a URL to a talk that I did last year about trying to find the right balance between self-service and centralized BI. You will find all the slides uploaded later on in internet, so you don't need to take screenshot as of now. On top of this, Oracle Analytics has what is called augmented analytics. So first of all, it does data enrichment suggestions. We will see the details later, but basically the tool itself suggests us which transformations we should do on top of the dataset that we are analyzing. Then we just one click, I can right click on a line chart and just create a forecast of like 5 other months, for example, just with 2 clicks. Then I can just write, tell me the sales for my country, and the tool itself will generate the query and will create the graphs which are appropriate to the sentence that I was writing. Another important feature is Explain. Explain, as we will see later, will tell everything we need to know about the dataset that we are analyzing. And then there is also the option to do advanced machine learning. So to create train mode machine learning models with 1 or more different methods and check the results of this training and do predictions. So we understood what Oracle Analytics in the cloud is about. There is also the same capabilities as coming on premises since the last 15 days with Oracle Analytics Server. Now it's time to move and to look at what is a data scientist. Data scientist, I believe you started listening to the mythological figure of a data scientist a few years ago. And it's basically an unknown figure because everybody wants it, but it's very hard to find. So I went into the internet and tried to understand what is a data scientist. And this is from Wikipedia or like another website, I believe in this case. But basically, a data scientist is a person who does data analytics, who extracts insights from a data set and basically tries to identify pattern or strategic opportunities for his company. If you think only about this definition, a data scientist is basically just a data analyst who lives in California. This is just the extreme. But the reality about the data scientist is that it requires a lot of skills. A typical data analyst has the same substantial expertise on a specific field as a data scientist. What a data scientist most of the time has more than a data analyst is, for example, the mathematical and statistic knowledge, or the hacking skills, for example, the Python, writing Python, or the knowledge of the packages within Python that needs to be used in order to do data science. Still, this is a very simplistic version of what a data scientist is. There is another image that I like very much, done by Brendan Tierney, which is an Oracle ACE director and good friend. What you can see in this image is basically that data science is a very complex environment where to be. You need to have a lot of skills, both hard skills, for example, data mining, statistic, pattern recognition, but also soft skills about communication, presentation, or problem solving. The problem with this definition is that it's almost impossible to have all of this. And in order to define yourself as a data scientist, it will take a long time in order to know all about all these items. So what you can do, what we can do, what the world is doing is basically, from one side, we have the data scientists, which are people that are basically at this point of time rich because there is a high demand of them and there is not as much people that can compensate the demand. On the other side, we have companies missing data scientists, but they still have data science problems. They still want to start using data science, but possibly they cannot afford a data scientist or they are in a location where they cannot attract a data scientist. So how can we solve this problem? Well, with what I call the low-hanging fruit theory. Basically, if we have just a limited budget to hire data scientists, instead of using them to solve all the data science problems that we have in our company, we use them only to solve the most difficult problems. And then we enable all the data analysts to upskill to start doing data science by themselves. basically do what we call democratize data science, bring data science to people. Some examples. If I'm a business analyst, I want to understand what are the drivers of my sales. In the old school method, I was only understanding based on my experience. Based on my experience, I can guess that, for example, selling gelatos in August will create more revenue than selling gelatos in January. The problem with this is that it's strictly related to the personal information. So you have the personal bias in analyzing the information. What if with a tool, I could just connect to a data source and the tool itself could tell me, look, that the statistically significant drivers for your sales are A, B, and C. This removes the personal bias, plus it gives me a lot of knowledge that it will take weeks or months before I could get it myself. And this is what we call augmented analytics. The second use case is basically, I'm again in the business side. I want to, for example, optimize the number of calls that I can do in a day and optimize them in such a way that I'm calling only the customers that are likely to accept an offer. In the basic reality, here I'm starting from a 50-50 chance. The client is either going to accept or not my offer. What if with a basic machine learning model that I can create myself without the involvement of a data scientist, I can reach the 70% accuracy? This potentially is not a big figure, but just a business analyst working by itself can potentially raise 20% the amount of successful calls that can do in a day. So Oracle Analytics Cloud can solve both of the problems, both of the use cases that I've been talking about. And now what we will see in this third part of the webinar is how we can start our path to data science with Oracle Analytics Cloud. We will see together a set of steps that any data scientist does. Sorry, just a second. That any data scientist does when approaching any data science problem, and we will see how we can do the same with Oracle Analytics Cloud. So let's start. First, the very first item that we need to do is define a problem. There is no general purpose data science or machine learning. We need to define a problem in very precise terms. An example is predicting wine quality. I want to understand and predict if a wine is good or bad. How can I define a problem? I need to use the acronym TEP. T stands for task. I need to tell what I'm going to predict. What is the action that I want to predict? In this case, I want to classify a wine in either good or bad. The second is experience. Basically, I need to know which is the history, the backlog of information that I'm starting with. In my case of wine predictions, I had a backlog of wine description together with associated rating that I could use in order to classify a wine as good and bad. And then P, I need to understand and define which is the performance that I want to try to optimize. In this case, I want to optimize, for example, accuracy. And this is one of the several different performance metrics that you can use to measure different machine learning models. Once I define my problem, the next step is I need to connect to the dataset. And OAC does a very good job because, as we said before, gives you the opportunity to connect to both predefined data models that your IT department created for you, as well as external data sources. So I can use for example, the revenue for my company, which is curated by my IT department, together with some other data which is coming from an Oracle database that I can connect to, a Postgres database, a Dropbox containing Excel files. I can connect to both and I can mix and match informations. Not only I can connect, I can also select which columns from which data set I want to use, and I can also apply some filters if I want to exclude some data. Once we connected to the data source, it's time to clean. This is a slide that I use every time. What we all think a data scientist does is possibly work on models, try to optimize the models, try to understand which features work best for a model. The reality is that data scientists spend most of the time in cleaning data. There are several, this is just one, articles in the web telling that most of the times the data scientist spends 80% of the time cleaning data and only 20% working on the actual model itself. So what we have to clean? I'm showing you several things that a typical data scientist does in order to clean a little bit the data. First of all, missing values. What do we do if we have missing values for a particular dimension? Do we delete the record? Do we substitute with the default value? Do we substitute with the average value of a specific metric? What we do with wrong values, you can all tell in this case that both mark are the same. But if we don't, for example, do an uppercase, the machine learning model will treat the two values as different values. There is no magic in machine learning that avoids you to do a wrong estimate based on a slightly different version of the same value. Then we may need to remove some observations which are not relevant. For example, if we are trying to predict the traffic in Milan, should we keep the data of the traffic in Rome within our dataset, or is that going to create fake predictions or have a less accurate prediction for our model? Then we should label the columns. Most of the times when you connect to a raw data source, the columns are named column A, B, and C. If you feed the machine learning model with column A, B, and C, the machine learning model will just produce some predictions. And the machine learning model will not care less if you have a column labeled called A or person name. Labeling columns is especially useful for you because then you will be able to explain, look, that my machine learning model is using the person name as good indicator for my prediction instead of is using column A as good indicator for my prediction. So labeling columns is useful for you to explain why the machine learning model took some decision and is using some columns in order to create a prediction. Then another important step is handling outliers. In this case, I'm trying to, for example, to predict the salary of a person within the company. Should I include within my data set the salary of the CIO, which probably is way out any other salary within the company, or should I exclude them? We need to analyze, understand outliers, and define an action to either include or change them somehow. Another important thing is feature scaling. Some of the machine learning algorithms are working on what is called the Euclidean distance, meaning that they will try to optimize the distance between the prediction and the actual point. What feature scaling does is basically put all the features within the same scale. So the machine learning algorithm will try to optimize all of them equally. Then, especially when connecting to raw data set, we may want to do aggregation. So for example, if we have the click stream, we may want to aggregate by user and calculate the number of clicks by user in a specific session. Lastly, we may want to split our dataset in train and test dataset so we can train our machine learning model and then test the machine learning model with previously unseen data in order to understand if the model is good enough to handle new observations. So how do we clean? If you see all the cases that we explained before with an ETL toolset in mind, you can immediately understand that data flows, the component within OSC that is creating mini ETLs, allows you to solve almost all the problems. It allows you to do filtering, aggregation, joining, binning, grouping. You have a lot of options with data flows. So let's look at the examples. If you think about them with an ETL point of view, it's all a set of standard ETL transformations. So we have case when, upper, filter, column rename, feature scaling is a division between the difference between the maximum and the minimum, counting, filtering. And the good thing with OSC is that some of the cases are automated by the tool. So with OSC, you don't actually need to do train and test set split. It's already done by the tool. Feature scaling, again, is something done by default when creating a machine learning model. The same, you have a lot of options to handle automatically the missing values. What about the outliers? Filtering the outlier, the point about outliers is that we need to identify them and possibly filter them out. Filtering a specific point out is very easy once we understand what the point is. So let's have a look at why removing an outlier is necessary. It's the same case as I was talking to you before. We want to try to predict the average salary depending on the years of experience within a company. We have the table on the left, which for every year, it tells us which is the current average salary within the company. You can see that the row number 10 is way out and is the only person who was in the company since the beginning, who now is the CIO. The two models that you can see are using the same parameters. The top model is fitted with all the data points, so including the salary of the CIO. The bottom data model is fitted only with the other 9 points, the other 9 rows in our data set. You can see immediately that the top model is way less accurate than the bottom model. So identifying the outlier and removing them from the data set is going to improve our accuracy in the predictions. How do we find the outliers? If we have one dimension, we can plot the dimension, and OSC will already tell us some facts about the dimension. For example, in this case, I have a range between 0 and 100, but the average value is 87. So it's moved towards the end of my data range. So I can plot this image with OSC because it's a tool that allows me to plot any kind of data. And I can immediately spot, for example, some null values all to the right, and some outliers, which are values, in this case, less than 25, where the most of the rest of the data set is between 80 and 100. I can use this data now in order to filter potentially the rows in my data set to remove the outliers. And this is working well with one dimension. What if I have more than one dimension? With 2 dimensions, I can create a scatter plot. And with OSC, I have an option to say, just right-click, add outliers. OSC will immediately divide my dataset in outlier and not outlier, and I can use this information in order to remove what OSC marks as outlier. So we understood how to connect, how to clean. Now it's time to do transform and enrichment, or like data scientists call it, feature engineering. For example, I have a location, I want to calculate the zip code. I have 2 locations, I want to calculate the distance between them because it could be a good predictor. Just imagine the case that I want to predict the taxi fare between 2 locations. Knowing the distance between the 2 locations will be a really good predictor of the amount that I will have to pay to the taxi driver. If I have the name of a person, I want to maybe understand the sex of the person. If I have day, month, year in multiple columns, I want to include them in a unique column called date, for example. You can immediately understand that the 2 transformations on the right are easily achievable with data flows again. They are pretty much standard ETL transformations. On the other side, the 2 transformations on the left, with almost all the other tools, you will need yourself to find an additional data source that, for example, matches the location to the zip code. And you will have yourself manually to join the dataset containing the location with the dataset containing the location to zip code mapping in order to extract the information. Or the same with the name and the sex of the person, you will have to find a dataset that translates names to the related sex. With OSC, you don't have to find any additional data source. OSC has a step which is called data preparation recommendation, that for every column in your dataset, it will suggest some transformation. So if it finds that we have a first name in our dataset, it will suggest that we add the sex of the person. If we have a location, it will suggest, should I add the zip code? Should I add the capital? Should I add the continent? So it will enrich automatically or suggest us some automatic enrichment in our dataset. Even more in the future, you will have the option to basically say, every time you find a product ID within my dataset, suggest to use my golden product dimension to enrich the dataset with product category, brand, subcategory, etc. If you don't need to do spatial enrichment, so if you need, for example, like in this case, to understand which are the customers that are less or more than 20 kilometers far from any shop of my company, you have now a tool called Spatial Studio, and there is a URL at the bottom of a blog post that I wrote about using Spatial Studio that allows you to do this kind of transformations in a visual way, and is easily you can combine easily the results of any data Spatial Studio query with Oracle Analytics Cloud. So we understood how to do the feature transformation. Now it's time to deeply analyze our data set. If you have some experience with data science, you will know that one of the first things that the data scientist does is have an overview of the data. And we have the same with OSC. Basically, it tells us all the columns that we have in our data set, what's the data type, and also it gives us some sample values. On top of this, we can click on any column within our data set and say, explain me this column. OSC will immediately start generating some information on top of this column. It will show us all the, basically the distribution of the column, the distribution of the column values for each of the other dimension. And also it will tell us the key drivers. So it will tell us, look, that within your data set, for the column that you are trying to explain, for example, I want to explain if a wine is good or bad, you should use the price and the region too as features in order to create a machine learning model to predict the quality of the wine. So it's solving also partially what is called feature selection for us. Once we understood which features we need to use to create a predictive model, it's time to do model training. What problems are we trying to solve? Basically, with OSC, you can solve two types of machine learning problems. First is called supervised, where basically I have a history of the solution that I want to implement, of the value that I want to predict. And I will use this history in order to feed the model. On the other side, I have unsupervised problems where basically I have a data set and I need the computer help to make sense of it. For the supervised, I can solve problems which are called regression, where I'm trying to predict a continuous numerical value, or classification, where I'm trying to split my dataset in two or more classes. For unsupervised, as of now with OSC, you can solve clustering problems, again, where you are trying to split your dataset in two or more classes without any prior knowledge, based only on a set of features that you are including in the dataset. How can you do that with OSC? Well, you have several ways. The first way that I'm showing you now is what I call easy models. Basically, let's say that I'm the chief of football team in Europe. Football stands for what Americans call soccer, but it's football, of course. and I want to buy a new wing. I know by experience or because the tool told me that crossing and stamina are the two most important features that I need to evaluate to find a player. I can immediately plot them in a nice scatter plot, and I can use, for example, the price of a player as further filter in order to filter down all the players that that are visible in my dataset. But this is not enough. I want more information. So what I can do is I can right click and select, say, add statistic, and I can select clustering. I have the option that you can see at the bottom right of selecting which is the algorithm that I'm using and how many groups I want to create. This way of clustering will basically use the stamina and crossing to create, in this case, 5 different groups in order to find common groups within the players. Possibly me as owner of the team, I will try to pick someone in the purple zone, which looks like the most interesting part of the wings. I call these easy models because, as you see, it's just one click away. The only drawback by using these easy models is that it will create, in this case, a clustering algorithm based only on the dimension that you are plotting in the chart. If you want to do something more advanced, OSE gives you another option. Before that, you can achieve kind of deep knowledge about your data set also by generating natural language. This text that you can see here is automatically generated by OSE based on the same stamina and crossing and player name that I was showing you before. In this case, it's already telling me that, for example, I should look to buy Gonzalez, Bauer, Correa, because are the best players for the values that I'm analyzing. As you can see here, it's giving me very good predictions, but only analyzing stamina and crossing. What if I want to use more? I have the option to create custom machine learning models with a set of features that I define in data flows. Data flows, you can find a train model section where you can train a numeric prediction, multi-classifier, binary classifier, or clustering. Every time you select basically which problem you're trying to solve, it will ask you which model, which type of algorithm do you want to use for model training. And then every time you select one algorithm, it will ask you which parameters you want to use to fit the model. As you can see at the very bottom, you can select which is the training partition %. So it will do training and test dataset split. It will allow you to handle null values with the categorical column imputation or the numerical column imputation. So it does a lot for you instead of you having to clean the dataset yourself. The problem here is that which parameter should I choose? What will be the best set of parameters for my problem? Well, the reality is that there is no golden rule for this. Maybe a data scientist will have in mind some sort of best parameters, but there is never a golden set of parameters that will always work for any type of data set. So what you can do with OSE, you can iterate. You select a model, you select some parameters, you store the data flow that will create the model, and you store the model itself. And then you start again. You change some parameter, you store the data flow with the new set of parameters, and you store the model with the new parameters again. The good thing about OSE is that it will allow you to compare several different algorithms by giving you the same sort of confusion matrix in this case. So it will tell you how many good and bad predictions you created. In this case, good predictions is where we have a smiley face where the predicted and the real value are good. Bad predictions is where basically is not good and bad. It's basically missing and not missing, matching and not matching predictions. And then it will give you also some aggregated data that will help you evaluate which machine learning model is better for use case. In this case, we have 2 machine learning models. Depending on which is the KPI that we want to optimize, this will basically drive the decision of our model. If what we are trying to optimize is just the predictive value 1, actual value 1, well, the first model is much more accurate for our needs. So we will choose the first model. If on the other side, for example, we want to understand how many good predictions we did predicting 1 on top of all the predictions, well, the first machine learning model will have precision of 64.09, while the second model will have precision of 64.77. So we will select the second one. So based on which is the KPI that we are going to use in order to evaluate our model, this will also drive the decision of which model we are going to pick to do our predictions. This was the confusion matrix is a typical case of classification where we are trying to classify a row either in 2 or more classes. When we are trying to predict a numerical value, it's called regression, as I said before. The same way, OAC will give us the same sort of KPIs to compare multiple models. In this case, it will tell me, look at the root mean square error, so the average distance from each prediction to each real point. In the first case is 3.22. The second case is 3.16. So maybe if the root mean square error is the KPI that I'm trying to minimize, the second model works better compared to the first one. So now we understood how to connect, clean, do feature engineering, analyze the data, train a model, and evaluate multiple models one against the other. Now it's time to predict. With OAC, I can use it on the fly. Basically, I'm analyzing a set where I want to create predictions. I select create scenario. I select which model I want to use. I need to map the columns that I use to train the model with columns coming from this new data set. And then I can start using the predictions immediately in any visualization. This works, however, you have to keep in mind that using on the fly will basically do the predictions for every different graph you are plotting. If on the other side, you want to run the predictions once for your target data flow and then store the result, you can do that with data flow. You select the step apply model, you select the model, you do the same column matching as before, and then the target dataset is created and stored for you. So if you can do all the steps that we discussed so far with OAC, well, congratulations, you can do what data scientist does. So you could potentially could call yourself a data scientist. Well, the reality is quite different. As I said before, data science is very complex. The required knowledge that you need to have in order to solve a problem is increasingly difficult. So we started for a classification problem with 0 knowledge and 50-50 chances of getting the right result. With a little bit of knowledge, we can raise easily 60%. With tools like OAC and some more knowledge about data science, we can create a predictive model that predicts correctly 80% of the cases. But from here to go something like 90, 95, 97, 99, depending on the use cases, the amount of knowledge that is necessary is huge. And possibly also OAC is not the best tool if you want to scale up a lot your precision or in case of handling huge amount of data. So what you can do, you can start using other tools, but before that, you already start understanding some concept of data science, like data cleaning, all the steps about missing values, transformation, or feature engineering, how to take 2 or more features and combine them together in order to create a feature which is a good predictor for your problem. At the same time, you understood how to do model creation and evaluation, and also how to select the feature which should be relevant for your machine learning model. all these items are key to any data science project. So even if you're not achieving the 99%, you are still learning, you're still starting your path into data science. And at the very end, even if you're not achieving the 99%, even if you're creating a model which has only 80% accuracy, that model is much, much better from the starting position that you had earlier in the day, which was 50%. So even if you are not a data scientist, but you can create values for your company with the same set of tools that you are using in your day-to-day job, you are doing something positive. At the same time, as I said before, when you need to achieve like 99% accuracy, when you need to work on top of huge data volumes, well, then it's time to request a data scientist, because he will probably know how to handle those situations. At the same time, especially when working on huge data sets, instead of extracting data from a source system and doing the transformation in the analytics system, it's probably a good idea to push the machine learning to the data. And if you are in the Oracle world and you're storing the data in the Oracle database, well, you are lucky, because there is a set of tools called Oracle Machine Learning that is doing exactly that. So you can, as of now, create models with just pure PL SQL. Or if you are passionate about R, you can do the same with R, and Python is coming soon. So you can run, you can do your machine learning pipelines directly in the database using the power of the database, and without the data leaving the database anytime in your pipeline.